In this video, we're going to determine whether two given planes are parallel, perpendicular to each other, or neither. And if they are neither, we want to find the angle between the two planes. Let's start just by drawing some pictures. Okay, if the planes are parallel, for simplicity, let's make them both flat, like the XY plane. So here's plane 1. Here's plane 2. Let's give plane 2 a normal vector. Let's give plane 1 a normal vector. Call it N1. If those two planes are parallel to each other, I think you can see just from the picture that their normal vectors are parallel to each other. This is provided, of course, that they're parallel, and then they're also not the same plane. We're thinking of two different planes. If we've got two different planes that are parallel to each other, their normal vectors are going to be the same. So plane 1 is going to be parallel to plane 2 if and only if the normal vectors are parallel to each other. And remember our test for parallel vectors. I mean, we could take the cross product and show it's 0, but that's pretty complicated. The simplest way to tell that two vectors are parallel is to see if they're constant multiples of each other. So if n1 is just a constant times the vector n2, you know the planes are parallel to each other. So that's what happens if they're parallel. Now let's imagine that the two planes are perpendicular and see what that tells us. So I'm still going to draw one plane flat. I'll call that one plane 1. And then perpendicular to that, we want to draw plane 2. I'm going to try to draw this with some perspective. Doesn't have to be perfect, you just do the best you can. That's plane 2. And these are meeting at a 90-degree angle. Now notice that when the planes are perpendicular to each other, the normal vector to plane 2, it looks like this. Or I could draw it in the plane of plane 1. Looks like that. And the normal vector to plane 2 or plane 1 looks like this. Or similarly, I could draw that in the plane of plane 2. So those two planes are perpendicular if and only if their normal vectors are perpendicular. And I'm using the word perpendicular to mean they meet at 90-degree angles. Of course, we say vectors are orthogonal, planes are perpendicular. But I'm still going to use that perpendicular notation from geometry class. So plane 1 is perpendicular to plane 2 if and only if, so that means the implication goes both ways, the normal vectors are orthogonal to each other, or they meet at a 90-degree angle. And do you remember the operation that tells us that two vectors are orthogonal to each other? That's dot product. So if these guys meet at a 90-degree angle, then the dot product between them has to be 0. Okay, so those are two extreme cases. It looks like the planes are parallel to each other if the normals are parallel, and that means that one normal vector is a constant times the other. The planes are perpendicular to each other if the normals are perpendicular or orthogonal to each other. Now let's think about the third case, third possibility. What if neither of those is true? I'm still going to draw that one plane flat as I can. And then I'm going to imagine another plane that's meeting it at an angle. So maybe it meets it at an angle like this. Oh, this is hard to draw. It's very, very hard to draw. Let's make it a little bit less steep. And try again. So let's say that's part of that plane. And the rest of it is going to come down like this. Yeah, this one's hard to draw. Okay, I think you get the idea. Sorry about that mistake over there. That's what happens when we're trying to draw 3D things in 2D. We do the best we can. So this red plane is plane 2, and this is plane 1, and we want to know maybe the angle between those two planes. And in order to find the angle between those two planes, it's helpful if I change my perspective. You can see the direction that we're looking at this from. We're looking at it from a direction where we see this line and this line, but we also see like the surface of that plane, and we see the surface of this plane. But if we walk around so that we're over here, like looking at these two planes meeting from this side, there's going to be a certain perspective when this looks just like a line and that looks just like a line, where we don't see the 2D part of this. We just see two lines intersecting. So like we are facing that, like that's the back of my head, that's my hair, and I am looking at those two planes intersecting just in 2D now. So from that certain perspective, plane 1 might look like this, and plane 2 might look like this from that perspective. You say, okay, and we're trying to find the angle between the two planes. Now it turns out the angle between the two planes is related to the normal vectors, very similarly to what we saw up there. We said the two planes are parallel when the normal vectors are parallel. Two planes are perpendicular when the normal vectors are perpendicular. So, well, what's the angle between the two planes? Well, just like we see up here, it turns out that the angle between the two planes is given by the angle between their normal vectors. So just to show that, to demonstrate that, I'm going to draw the two normal vectors on this picture. Plane 1's normal vector I'm going to call N1. I'm going to make it very long just so that we can see it. So that's N1. And N2 is perpendicular to plane 2. I need a straight edge. I'm making a straight edge out of another piece of paper here. Okay. All right. So the normal vector to plane 2, like one of them is going to go down, the other one's going to go this way. And try to draw it like that. And that's at a 90-degree angle to plane 2. That's N2. Okay. And don't be distracted by all those labels from the other picture. Like that all goes over here. Now we're just focused on this picture right here. That's N2. And the question becomes, well, what is the relationship between those two normal vectors? I claim that angle between the two planes is the same as the angle between the normal vectors. And I think it's pretty easy to see. Since N1 meets plane 1 at a 90-degree angle, if that's theta, let's say it was 30 degrees, what's that angle going to be? If you said 60 degrees, you're right. It's going to be exactly what I would need so that these two angles add up to be 90 degrees. So if that's theta, this is going to be 90 degrees minus theta. And then I've got a right angle right here. It's a right angle on this side, and then there's also, of course, another right angle on that side. So we get 90 and 90 is 180 degrees on a line. And the question becomes, well, what's the angle between the normal vector to the second plane and normal vector to the first? Well, this vector plus this, or this angle plus this angle has to equal 90. This plus this is 90 if that's theta. theta plus 90 minus theta is going to give me 90. So we see from this picture, when I look at it from just the right perspective, so I look at it so I'm just seeing one end of the plane and another end of the plane, I can see that the angle between the normal vectors is the same as the angle between the two planes. And if I want the angle between the normal vectors, well, if I know both of the normal vectors, we can use the dot product. If I take those two vectors and I dot them, I get the length of the first times the length of the second times the cosine of the angle between them. The angle between them is theta. If I have these in component form, I can compute the dot product, I can compute the lengths. The only unknown in this equation is theta. So we would divide by the product of the lengths and take the inverse cosine, or arc cosine. Oops, that should be that, and that should be that. So this is our formula for theta. Okay, so if they're parallel, we have this. If they're perpendicular, the dot product is 0. If they're not perpendicular and they're not parallel, we can use this formula to find the angle between the planes. Okay, so now let's go back to our question. The question says, determine whether the planes that are given here, given their equations, are parallel, perpendicular, or neither. And if they're neither, we want to find the angle between the two planes. Well, first of all, let's read off the normal vectors. Now remember, general form of a plane looks like this. AX plus BY plus CZ equals D. And we derived that by taking the dot product of the normal vector with a general vector in the plane that went from x naught, y naught, z naught to a point x, y, z. And after taking that dot product and distributing and moving all the constants to one side, we got this. So A, B, and C, those were the components of our normal vector. So if I'm given an equation of a plane and I want the normal vector, all I have to do is read off the A, the B, and the C. Same thing here, I have to read off the A, the B, and the C. So the normal vector to plane 1 comes from the coefficients of x, y, and z on plane 1. So there's a 3, a 2, and an implied -1. That's our first normal vector. Our second normal vector, the normal to plane 2, I'll write that n sub 2, or n2, has an implied 1, -4, and 2 as its components. Okay, are those multiples of each other? If I multiply this by something, can I get this? You say, no, Miss Townsend, I can see that that's obviously not true. You say, okay, well, what's an algorithm? What's a way that I can prove that it's not true? Well, the first thing I can do, if I want to prove these are not parallel to each other, I think it's obvious just from looking at it. But if I want to prove it to myself, I can say, what do I have to multiply this 1 by to get that 3? Well, I'd have to multiply it by 3, right? So the only way these two could possibly be parallel is if this times 3 was this. So I'm just going to compute 3 times n2. You don't have to do this. If you can just look at them and say that's not a multiple of that, that's enough of an explanation for me in this class. But some students, they really want an algorithm. They want to know what they have to do to check. If we multiply this vector by 3, we get 3, -12, 6. And that's not the same as 3, 2, -1. That's not n1. So that was the only possible parallel vector, and it wasn't parallel. So n1 is not parallel to n2, which means plane 1 is not parallel to plane 2. Okay, So let's check to see if they're perpendicular. So that was the first part. They're not parallel. If I want to determine if my planes are perpendicular, I'll have to take the dot product of their normal vectors and see if I get 0. So let's do n1 dotted with n2. Remember how this works. You just multiply component by component, and then you add. So we'll do 3 times 1, and then add 2 times -4, and then add -1 times 2, and I get 3 minus 8 minus 2. So it's 3 minus 10, which is -7. That's not 0. If it's not 0, then we know that the angle between the two planes is not 90 degrees. So n1 and n2 are not perpendicular to each other. That means the planes are not perpendicular to each other. Okay. Now the last possibility is if they're not parallel and they're not perpendicular, there's some other angle between the two planes. It's not 0 or 180 or 90 degrees. To find the other angle, we're just going to use the geometric definition of dot product and solve for theta. So we needed the dot product. And we got -7. Remember what that tells us? That's negative, so the angle is going to be obtuse. At least given the two normal vectors that we read off of the equations. Then I need the length of n1, or the magnitude of n1, and the length of n2, magnitude of n2, same thing. n1 has components 3, 2, -1, so we square them, add them, and take the square root. We have 9 plus 1 is 10. 10 plus 4 is 14, so we get the square root of 14 there. Do the same thing with the components of n2. We're going to square them, add them, and take the square root. That's 16 plus 4 is 20. 20 plus 1 is 21. The square root of 21. Now if you want, you could simplify the dot product divided by this length and this length. You don't have to though. But theta is the inverse cosine of the dot product, which is -7, divided by the length of n1 times the length of n2. And I think some of you probably see it. You probably want to simplify that too. 14 is 7 times 2. And this is 7 times 3. So we're going to have a square root of 49 in the denominator. There's going to be a 7 down there. You don't have to simplify that if you don't want to. So we have 7 times the square root of 6, and those reduce. So it looks like we've got the inverse cosine of -1 divided by the square root of 6. And I would get my calculator out and evaluate that to figure out what my angle theta is. Just stepping away for a second to get my calculator. There we go. Okay. So I have the inverse cosine of -1 divided by square root of 6. And so the angle between those two normals is 114. .09. And I'm in degree mode, so that's degrees. You'd say, okay, well, what does that mean, Miss Townsend? Well, let's say that this one plane is lying flat like this. Then the other plane, who meets it like this, actually 90 degrees is here, and I want to add about 25 degrees, so a little bit less than a third. So that would be like a third. You can do a little bit less than a third. This is plane 2. And what we just found was the angle between the two normal vectors that were given was 114 degrees. So that's actually going to be this obtuse angle, 114.09 degrees. Now that might not be the angle that we're looking for. Most of the time when we talk about the angle between two planes, we're talking about the smaller one. So this formula didn't give us quite the right answer, but it gave us a reference angle. Whenever we talk about the angle between two planes, we want the smaller one. So this is the answer. So this is going to give you the exact right answer if theta is acute, because we want the smaller of the two angles. Now, if theta is obtuse, or if this theta is obtuse, if the angle between n1 and n2 is obtuse, then we want the angle between the two planes. In that case, it's another angle. And I want to call it a different name. I'm going to call it alpha. Alpha is going to be 180 minus that theta from up there. Or if you prefer radians, pi minus theta. So I think I'm going to stay in degrees because it's easier for me to think about. If I take that 180 degrees and subtract the 114.09, that's going to give me this angle right here, 65.91 degrees. That's approximate. So this is your formula for the angle between two planes, when the angle between the normal vectors is obtuse. You might say, Miss Townsend, I thought you went through that whole derivation and you told me that this was the angle between the two normal vectors. Yes, this is absolutely true. That's going to be the angle between the two normals, provided that we draw our normal vectors this way. You've got n1 pointing this way and n2 pointing this way, so that the angle between them is acute. But don't you all agree that I could have just as easily drawn a different normal vector for that second plane? I could have drawn this one instead. I'm going to call it n2 star. Now the angle between n1 and n2 in that case is obtuse, but the angle between the two planes, it's actually the smaller one. It's that angle there. That angle is equal to that angle. This obtuse angle, it's also an angle between the two planes, but it's not the one we mean. Whenever we talk about an angle between two planes, we're talking about the smaller of those two angles. So the angle between the two planes in this case is not that. but it's 180 minus that obtuse angle, which is about 65.91 degrees.